Yes.
Could you please mute yourself? Since I think you can mute you now. Sorry. Okay. Welcome to the session Forecasting and Nowcasting. My name is Max, and I'm going to be your chair today. And today, I'm delighted to announce that we have 4 wonderful talks scheduled. And during each talk, the audience may write questions in the Q&A tab, which you will see on the right-hand side. And the speaker may either respond verbally after their presentation or by typing in the Q&A tab. Every presentation has at most 15 minutes, followed by 5 minutes of discussion. So without further ado, I propose that we get started now. Our first speaker is Kapil Chutari from the Indian Agricultural Statistics Research Institute in New Delhi. Kapil is a PhD scholar and is currently working on decomposition-based deep learning models for agricultural price forecasting. Kapil, the floor is yours. You may start sharing your slides now.
Thank you, Max. Is it okay?
Yes, you can see it now, and now it's full screen. Excellent, you can start.
Welcome all you for this session forecasting and accounting. For the presentation is VMD for agriculture price forecasting. These are the content of my today's presentation, where first of all we will discuss what is the time series data, what are the problem of agriculture price for different models we use for agriculture price forecasting, and what are the limits of this forecasting model, and after that is today's need for the time. Next, in time series decomposition, we will discuss different type of technique, and after decomposition we have to forecast each decomposed part. For that we have used time delay neural network, which is part of artificial intelligence, and after that we have taken soybean oil from world market purpose and conclusion and references. So actually time series consists of a set of observations which are ordered in a time for a given phenomena, and time series analysis extract meaningful information or statistics from a given data. And price forecasting is a major aim or goal. In the price forecasting, there are different forecasting for financial time series data and everything we do, but commodity are different from all these price for other forecasting, because agriculture commodities are more vulnerable to their supply side, so due to perishable and many abiotic and abiotic. There is lots of research review of literature that suggests use different forecasting model for agriculture price forecasting, but still we cannot achieve that much of accuracy model. So here we use decomposition based time delay data. Here first of all we have to decompose a series into different part. Decomposition we have forecast each and individual component. So for the decomposition we use Fourier transformation, empirical mode decomposition, ensemble empirical mode decomposition, and variational mode decomposition. All these decomposition are on the frequency part. So in Fourier transformation, mathematically signals are between the frequency and like sine and cosine are, but limitation that data should be linear and stationary, and assume that the all that form in sine and cosine form. But whenever we come to in agriculture commodity, there is may not follow the second assumption that the data should be in sine and cosine due to their highly volatile in nature. So for more decomposition, which is more data adaptive technique which we use, and it is mainly used for a non-linear non-stationary data series, complex price series we use. And first of all it decomposes series into different mode that we call a intrinsic mode function and a residual. And after that IMF have different amplitude and frequency modulation of a given data set, and IMF are orthogonal. If sum of all these IMF and residual, we will get original series. So here as we can see that a nonlinear and non-stationary time series is given. First we use EMD, and EMD decompose is IMF and residual. But EMD also limitation that the single IMF contains different frequency and single frequency broken into different IMF. Which weaken our physical meaning of and unable to implement feature extensions. Here we can see that it is your original signal. If we use EMD, then in first IMF it show high frequency and low frequency. In second IMF, as we can say, only low frequency. So actually it should be that low frequency in separate second IMF and high frequency in first IMF. But it is the limitation of the EMD. So to overcome these problem, next ensemble empirical mode decomposition EMD was used. We have to add original white noise in our original series, and if we add this noise, suppose we time at a time, that is our W is there, in N is there, that is our ensemble size. Now whenever we got a new to run EMD on each and every series, and after running WN time, we have to average to find out over a single IMF. So here, as we more decomposition. Here our IMF is here our low frequency separated into IMF2, and our high always kept in IMF. But VMD, EMD have always face a for mode mixing, that is if our low frequency and high frequency ratio is greater than 0.5, then again it is more mode mixing problem can be not resolved. And another problem is end effect. Actually in EMD we use an spline function to our or mode, but here as we can say it, the mode should be ended here, but it ended here. In the same way it is always ended here. So that is the end effect, means or at the point of end, or IMF or intrinsic mode function did not plot exactly point. That is the end effect problem. So variational mode decomposition, it is given by Drago, Smith and Joseph in 2014, and which is solve the current methods. So limitations such as lacking of mathematical theory, recurrence shifting process, and allow a backward hardband limits. Again, decompose number of mode on the central frequency. That is the part of the variational mode decomposition. That is VMD. Here, different method they use for Wiener filtering, Hilbert transformation, heterodyne demodulation, and ADMM. That is alternate direction method of multipliers are used to obtain these modes. So these are the basics which we use for the variation mode decomposition and through a optimization problem. Here, our main function is that summation of all these IMFs should be original series there. So Lagrange multiplier we use to extract all these IMF according to their central frequency. We have to minimize central frequency around first IMF to last. Suppose in first IMF we have highest frequency, but up to last IMF frequency is less than, but their amplitude is much more than. To determine this mode, we have to use two methods, that is central frequency method and signal difference method is there. In central frequency method, we can say that how we can say that this is number of mode we are sufficient. So suppose if we have it become two mode, means here central frequency difference is much more than, so we can't stop up to two. But in three mode, if we decompose our series in three modes, here we can say the difference is reduced. In four, again reduced. In five, reduced. Up to seventh IMF, six or seventh, there is no much difference. So we up to stay up to seventh IMF, because in last two IMF there is no difference on the frequency. So here we can stay, means there are seventh IMF are sufficient to decompose a series. Another method is signal difference average. It is nothing but, suppose I have decomposed my series into five parts, and I have sum of all these parts and subtract from my original series and average all these points, then it will be a negligible point. So here, suppose I decompose my part in number of mode, all this given, and after seventh IMF, it shows zero, means there after that nothing left in the data. So we have to constant on number of seventh IMF. But if we use less number of IMF than the seven, then here we can say there is an error showing. So we have to approach like in the second data. If we use 11th number of IMF, then that is sufficient number of data to decompose a given price series. After decomposition, for every IMF or every mode, we have to use a time delay neural network model, which is a part of a class of artificial intelligence. And here we have to decompose, we have to forecast each and every price series, each and every IMF, and give a forecasted value. And after giving a forecasted value of each and every IMF, we have to sum of all these forecasted value to give a final forecasted value. So these are the actually it is input series for my any series there is. It is based on PSA plot, that is partial autocorrelation function, and it give weight and bias to a hidden layer, and sum of all this weight is used to give an output for the output layer. There I use a different activation function, like in here we use identity function, in hidden layer we use sigmoid function. So these are the notation which we used for our time delay neural network. So, for illustration purpose, I have taken one data: international soybean oil prices, that is January 1916 to 2021, and from pink sheet there is a world market, and these are the basic descriptive of the data. And here, as we can say, that the number of observation I have taken 744 observation. These are the mean, maxima, minimum. These are basic descriptive, which shows the data is means highly volatile or not. After that, over decomposition's prerequisite concept is the data should be non-linear and non-stationary. Means data should be complex. Here complex means non-linear and non-stationary, for which we have taken two tests. That is, one is ADF test, another is Phillips Perron test. Both the tests are for used for non-stationary, and that is BDS test, Brock-Ditcher segment test, that is used. And all these tests show that the data is non-stationary and non-linear or soybean data. After this prerequisite test, we apply EMD method, and it decomposes series into 8 IMF and 1 residual. So our original series decomposed in all these IMF and residual. If we sum of all these IMF and residual, we definitely we get near to our original series. Again, if you use ensemble empirical mode decomposition, then it's showing that it again 8 IMF and residual. Actually, these number of modes, that is total number of IMF and modes, total number of IMF and residual is nothing but the log of T. Here T is my total number of observation. Here I have taken 744 observation. So nearly it is showing 8.7 and all these things. So means I have taken 9 IMF total IMF. Now
Kapil,
actually for the
you have 5 minutes left.
yes, what happened?
You have 5 minutes left. I just want to let you
Okay,
know.
okay, okay. I'm closed. So here in VMD, I have also used 9 IMF to show the same frequency and same amplitude. So after these, I have used different for means again. Suppose I have forecasted each and every series. Now I am feeding each and every IMF to our time delay neural network to forecast a given series. Here I have taken as a forecasting data set as a 12 month. Means 1 year I want to forecast each series. So forecasting evolution criteria, I have different criteria. That is, one is RMSE, MAP, D state, and double merino test. Here RMSE and MAP both are showing the error, and D state showing the direction, whether the price series is going in correct direction. Forecasted price series is going in correct direction or not. If it is in correct direction, then we will give value 1, otherwise it is 0. And for statistical test, we use the double merino test, whether the our forecasted model is good or not. So after these using forecasting evolution criteria, I have that use different model. That is, first, if I use only TDN model, then these are the RMSE, MAP, and D state. If I use EMD and EMD, then these are the MAP and RMSE and D state. And after whenever I use VMD, it is reduce everything drastically. Means here up to here we can say 30% reduction is there. So after testing all these criteria, now I go for double merino test, that is soybean test. Here every hybrid model showing that it is good. I mean, it is outperformed than a single model. And among the hybrid model, that is EMD, and VMD, over VMD perform outperform from each existing. So it is the package which I have developed for the VMD TDN model. Here, these are my advisory committee and everything. So its conclusion: statistical and machine learning based models are unable to forecast complex time series data. So for which we have used hybrid model, decomposition based model, and component based model and frequency domain have technique also used. Among the frequency, we use Fourier EMD and VMD, and TDN are used to forecast individual IMF. These hybrid model demonstrated their superiority over usual TDN model in difference of different forecasting evaluation criteria. These are my references which I have used for this presentation. Thank you.
Thank you very much for your talk, Kapil. If there are any questions from the audience, please write them in the Q&A tab. In the meantime, I could perhaps ask a question to you. Why do you think the hybrid methods are superior?
why I think superior hybrid method, because
Yeah.
in hybrid method na, it means every single component is taken by every individual model. So suppose I using only TDN model, means only NN model I am using, so it cannot capture the complexity. Means if I use only NN model, it will tackle only non-linear part. But whenever I use a hybrid model, it will tackle non-stationary and non-linear part. So I use EMD or VMD any part, it will simply decompose a series into different stationary and non-linear part. Now ANN will take easily tackle all these non-linear part. That's why hybrid is good.
Okay, thank you very much. There's actually a question in the Q&A tab. And the question is there a GitHub link for the latest version of VMD TDDN, so your package, since it's not on CRAN currently?
Actually, it is there in CRAN, VMD TDN. I
Okay,
have shown this. Yeah.
could you please paste the link in the chat so that Julia can access?
Okay. Okay.
In the meantime, if there are other questions, please post them to the Q&A tab.
Okay. Okay. I will paste it. Okay.
Perfect. Okay, let's see. Are there any more questions? If that's the case, please post them in the Q&A tab. Okay, so not at the moment, but if you should have any questions during the next few minutes, you can always post them in the Q&A tab, and then Kapil can reply to them by typing answers during the rest of the session. Okay, great. Then let's thank Kapil again for his interesting talk. And let's move on to the next speaker. Our next speaker is going to be Dr. Ronit Jaiswal, who works at the Indian Agricultural Statistics Research Institute. Ronit's recent work is focused on using statistical learning and artificial intelligence techniques to forecast agricultural prices. So Ronit, I would like to give the floor to you. You have 15 minutes. Okay.
Yeah.
So I think we can hear you. Excellent. So I think we're set to start.
Is it good?
It's good, yes. So we can hear and we can see you. So this seems to be okay. Great. Perfect. So we start when you're ready.
Okay. Welcome everyone. Computers are able to see, hear, and learn. Welcome to the futures. As rightly said by Dave Waters, professor of Oxford University. I am here to present on the topic STL-ELM, a decomposition-based hybrid model for price forecasting of seasonal agricultural commodities. As my good previous presenter already discussed the benefits and advantages of the hybrid model, on the similar lines, I am also going to present, but on the different data sets and with different models. So here are my contents. First, introduction. I will introduce you with the time series concepts and why agricultural price series forecasting is very important. Then I will tell you about, in briefly, STL, ELM, and then hybrid STL ELM model. Then I will illustrate the model with the real price data sets, then results, conclusion, and references. So start with the introduction. Time series is nothing but a collection of data from a continuous or discrete real valued process over a period of time. It has certain characteristics. For example, an explicit dependency on the time, obviously, noise and high dimensionality, lack of enough information, maybe non-stationary too. And the time series has several applications in research area. For example, forecasting and nowcasting, obviously, determination of transfer function of a system, analysis of effects of usual intervention events to a system, analysis of multivariate time series, and the discrete control systems. Agricultural commodities price series are very different from the most of the financial or crude oil price series time series. Agricultural commodity prices tend to be more fluctuating due to seasonality, inelastic demand, production uncertainty, and perishability. They normally follow a cobweb model, which leads to a price risk. Thus, there is a need to stabilize prices of agricultural commodities to enhance farmers' welfare. Further, it will also help producers to make better informed decisions and to manage price risk. However, in particular, vegetable price series are much more volatile and complex than the price series of other agricultural commodities. An important characteristic that exists in such series is seasonality, which regulates supply and demand to a great extent. Moreover, the perishable nature of vegetables further add complications in stabilizing their price. So based on different models, time series models, different researchers have tried to forecast agricultural commodities with different models. All these models are categorized into mainly broadly into two categories: statistical models and artificial intelligence models. In the statistical models, we have linear models like ARIMA and or Bot-Jenkins methodology, whereas in non-linear statistical models, we have fixed non-linear models. Both linear and non-linear statistical models have several limitations. However, one of them is that they pre-assumed a particular form of a model. However, in real data case, there is very much non-linearity and no fixed model is specified or relationship is specified among the data points. So, apart from the statistical models, we have artificial intelligence models, which works better than the statistical models, and the most uh, useful or widely used artificial intelligence models is artificial neural network. However, artificial neural network has also some limitations about poor performance for non-stationary series, and it has the limitation of local optima and very slow convergence. So why hybridization? So hybrid we have done on the lines of divide and conquer method, in which we take a time series or price series and decompose it into a simpler subsets or sub series. Each sub series consists simpler structure or stationary fluctuations. Now each sub series are easy to handle by forecasting models, and thus it is easier to get better forecast. So seasonal trend decomposition based on loss. This is a decomposition method we have used for breaking down a seasonal price series into different components. So a time series having seasonality in its virtue can be decomposed into STL method into its trend cycle, seasonal and remainder components. Thus, it gives three components: trend, seasonal, and remainder. The importance of Loess in the decomposition method is that it smoothens a time series by applying weights to the neighborhood of each data point according to the distance, and the polynomial regression is then fitted at each data point. This way of decomposition is, however, additive in nature, and after adding the components, it yields original series. STL entails two recursive procedures: inner loop and outer loop. In the inner loop, we have inner loop is nested within the outer loop, and in the inner loop, there can be several iterations. An iteration of the outer loop is, however, required only if there exist outliers among the data points. Suppose, let's say, monthly price it is decomposed by STL into trend, seasonal, and remainder. The whole procedure of the decomposition starts with zero estimate of trend cycle. Each iteration of the inner loop consists of this much of steps. In the first step, we use detrending method. In detrend, a detrended series is obtained from the original price series by subtracting its estimated trend component. Then sub-series smoothing. These detrended values are separated and collected month-wise to get 12 distinct monthly sub-series. And these sub-series are smoothed by a loss smoother. Here the loss smoother is used. And after smoothing, they are joined back together to form an initial seasonal component. Then it is passed to the low-pass filtering method, in which it is passes through by 12 moving average, and the result is again smoothed by Loess smoother. Thus, we are using Loess, the L component of the STL, for only smoothing purpose. Then, of the smooth series. The low pass filter values obtained in step 3 are subtracted from the initial seasonal component obtained in step 2 to get the actual seasonal component of the iteration. And then deseasonalization and then trend smoothing. These 6 steps are repeated until the robust estimate of the trend and seasonal components converge. Apart from this trend and seasonality, whatever left in the original series is residual. For the outer loop, these remaining components are analyzed and any extreme values or outliers among them are considered. These outliers are identified and a weight is evaluated. The weight evaluated is used in iterations of the inner loop to downweight the impact of outliers and found in the previous iteration of the outer loop. Then there comes the forecasting model, extreme learning machine. So what is extreme learning machine? ELM is an efficient neural network based model which is similar in the architecture of feed-forward neural network. In both feed-forward neural network and ELM, hidden nodes are initialized randomly, but the gradient descent and back propagation algorithm of a feed-forward neural network keep updating the parameters till the loss function is minimized. However, in ELM, the random values stay constant throughout the whole training process. And this novelty in the learning algorithm, is that the parameters or the weights that connect the hidden layer to the output layer are found by Moore-Penrose generalized inverse technique, which ultimately make the algorithm time efficient. So over the time delay neural network or feed forward neural network, the advantages of ELM is that it is extremely fast learning. It has extremely fast learning speed and superior generalization ability, both of which are prime importance when modeling through any AI models. So the whole procedure is described as follows. A simple series is decomposed into several samples. Then each sample is modeled using P input nodes and Q hidden nodes, and the weights here, whatever weight we have applied to the input series, is obtained by this matrix H, where this H is the Moore-Penrose generalized inverse, and this will give the minimum norm least square solution of output weight del hat. So the hybrid STL-ELM method. Given a price series YT seasonality, the modeling procedure of the proposed STL-LM method, 3 steps: decomposition, individual forecast, and ensemble. Hybrid STL-ELM method. So here we have taken normalized price series. Then STL decomposition will break this price series into trend, seasonality, remainder. Then each trend, seasonality, and remainder components are forecasted by the ELM forecasting model, and which are then ensembled to get final forecast of the original price series. This forecasting evaluation criteria we have used: root mean square error, mean absolute percentage error, diebold measurement test to statistically check the significance. And the data description, we have taken monthly wholesale price data of potato crop from the 2 major wholesale markets of India, namely Delhi and Kolkata. Price series of potato crop is chosen because of 2 main reasons. It is the most important vegetable crop whose demand is whole round the year, and it is very difficult to model and forecast them accurately as they are non-linear, highly volatile, complex, and exhibit seasonality, which is a real issue for growers, consumers, and policymakers. So these are the yes.
You have 5 minutes left.
Okay. So these are the time plots of Delhi price series and Kolkata price series. As you can see, the data is also itself telling it is non-stationary and having seasonality. So these are the descriptive statistics with mean, maximum, standard deviation, where we can see it is positively skewed. This Delhi market is leptocratic and this is platicratic. So this is ADF test. The results of ADF test is for checking the stationarity and non-stationarity of the price series. So we have concluded that both the price series are non-stationary. BDS test is used to check the non-linearity of the price series, and we have used the R package BDS test to check the non-linearity, and we have concluded that both series are non-linear. So this is the plot of the decomposition of the original price series, where the data is decomposed into trend, seasonal, and remainder using the STL decomposition method for the Delhi market, and similar lines for the Kolkata market. We can see easily it is showing seasonality. So these are the R codes we have used. We used to write for the whole analysis with for STL decomposition, then another forecasting. For forecasting using ELM. So we have developed a package by combining all the above codes with just a single function, STL-ELM, and by applying STL-ELM directly to the data sets, we can easily get the 3 components: seasonal, trend, and remainder. With the combining of them, we can get forecast and the different forecast error evaluation criteria also. So these are the seasonal indices of the Delhi and Kolkata price series, and we can see that from June to October, November, we can see there is a high price rise. And these are the other hyperparameters of the other optimized models like ELM and TDNN with the different input nodes and hidden nodes. to get the optimized results. The forecasting evaluation, since this is about the nowcasting and forecasting, so for the very near future, we have taken for horizon 1 also, for horizon 3 also, and for horizon 6 also. And with all these horizons, we have compared 3 traditional models or existing models with our STL-LM hybrid models with our package. And we can see that in all the 3 horizons, we can see STL-LM is performing better in Delhi market and Kolkata market. And we have also checked through the double mirror test also, and we found that HTL is significantly better at 5% accuracy level of significance with the ELM also, TN also, and 1% accurately than. So this is the package overall we have developed: STL ELM, STL TN, and STL ARIMA. So conclusion, this study examines the modeling and forecasting performance of STL ELM hybrid model in comparison with the existing forecasting models such as ARIMA, TDNN, and ELM using monthly wholesale potato series of Delhi and Kolkata. And we have observed that hybrid model provides better accuracy in terms of various evaluation criteria. The DM test also showed significant improvement in the predictive accuracy of STL-ELM model, and this work can be extended to develop and investigate the performance of hybrid models using STL with other possible combinations of forecasting models like LSTM, support vector regression, etc. for agricultural price forecasting. These are differences.
Okay, so I suppose you're done now, Ronit. Thank you so much for your presentation.
Thank you, Max.
You're welcome. Okay, are there any questions to Ronit? If yes, then please put them in the Q&A tab. In the meantime, I can also ask a question. So you've designed this forecasting method for with forecasting agricultural prices in mind, but I wonder, can you also use it for forecasting something else, which is also subject to strong seasonality or having a strong trend? So could I perhaps use it to forecast stock prices?
Yeah, anything, any time series or any data generating process which has seasonality, any particular seasonality, we can use HDL ALM for the forecasting of that series.
Okay, thank you very much. So let's see if there's anything in the Q&A. Maybe let's just wait for 1 or 2 more minutes. Okay. At the moment, there doesn't seem to be anything in the Q&A, but perhaps people will later use it to ask some further questions. So I would like to ask you to keep this only to keep this Q&A in mind. Perhaps people will come up with questions during the next talk.
Okay.
Okay, great. Thank you again for presenting. Oh, there's actually a question. Perfect timing. So the question is, would using STL improve the other benchmark models?
Yes, yes, definitely. It will improve any hybrid method will improve the other benchmark models. So we can apply STL TDNN also. Even I have applied STL TDNN and got the comparison very less. But here I have 2 purposes. One purpose is to check whether to show you the hybrid model is always better than the individual benchmark models. And second, the ELM is also better than the TDNN in terms of time and efficiency.
Okay, thank you for answering the question. And then I would like to move on to the next speaker. Thank you again for answering the questions and also to the audience for posing those interesting questions. And our next speaker is going to be Dr. Sam Abbott, who is an infectious disease researcher at the London School of Hygiene and Tropical Medicine. Sam's main research interests lie in developing, evaluating, and applying methods for improving our understanding of infectious disease dynamics in real time. Sam, I'd like you to share your screen, and then we can start whenever you're ready. Perfect, we can see it. Sam, are you talking already? Because we can't yet hear you. Perhaps you are still on mute. Perfect. Yeah, now we can hear you. Excellent. Perfect.
Excellent. Right. So I'm going to be talking about quite a big project that's ongoing on hierarchical nowcasting of counts with an application to COVID-19 hospitalizations in Germany. This is really my attempt to get contributors to the underlying R package EpiNowcast. So I really encourage you to check that out while I'm talking. And this is work, it's quite a large collaboration. I'm presenting lots of different people's work as my own, but it's work that I've done with Felix Gunther, Janis Bracker, Adrian Linson, and Sebastian Bunk. So keep that in mind. All the good bits are not mine. So I'm going to be introducing what the nowcasting problem is first, then talking through the Germany Nowcasting Hub, which is an interesting collaboration that I've been part of. Then introducing the underlying model for the EpiNowcast R package, introducing some details about the EpiNowcast R package itself, extensions that we are planning and that we're quite excited about, and then summarizing what we've done. So first of all, introducing the nowcasting problem. So what is nowcasting and what is it in an infectious disease context? Because it's quite widely known. So in infectious disease data, everything is really driven by an underlying infection process, and those are pretty much always unobserved. So what we end up observing are downstream proxies like onset of symptoms, test positivity, hospital admissions, and deaths. And all of these are delayed by some delay distribution. And we may be also interested in how these things relate to each other. So for example, we may be interested in onset of symptoms, but we may only observe their report date. And all of these things mean that there can be truncation when we're observing them in real time. So the core aim of nowcasting is to reconstruct these latent unobserved values, so infections, and then downstream proxies of infections that are observed with truncations due to their delay. And the reason this is important is it's really important during outbreaks for situational awareness. We've seen that a lot with COVID. There's currently ongoing work with monkeypox, for example. It's really important potentially to estimate what these underlying distributions are so they can be used in other forms of modeling. And then also it's very likely that if we use the partial data we have from Nowcast, it will improve our ability to forecast, which is, as I'm sure people are aware, a real challenge in infectious diseases. So the German example, the key here is we're looking at 7-day hospitalization incidents. And why, I hear you asking? The reason is because this is the key measure that was used to set policy in Germany. So it's important that they have a real-time estimate in order to make effective health policy. And it's indexed by date of by date of positive test, but it's available by date of report. And that means that the date that you see in a given week, those aren't hospitalizations that necessarily have been reported in that week. And that's where the truncation comes from. So this is what we might typically end up observing after a long period of time. So this is a fairly classic looking set of epi data. But unfortunately, in real time, we actually have this. So this is starting from left to right and is showing it being progressively updated, with the black data being the most up-to-date data. So orange, it clearly gets adjusted up, and then red, adjusted up, and so forth and so on. And this is the modeling challenge. This is what we're trying to do. We're trying to reconstruct black from all of these individual snapshots that we observe over time. And for example, for green, we'd use the snapshots from blue, purple, red, and orange to reconstruct how green maps to black. And that's basically the nowcasting problem in a nutshell. And what we might end up with is something like this purple line. So this is reconstructed what we expect to observe once we've reached a very long time away from what we're observing now. And then we can reconstruct that, we can make better decisions now. Well, at least that's the idea. And an additional complexity in this data is its age and region stratified. So there's some quite clear differences here between different age groups. And then it also has a really strong day of the week signal, which is something we see across a lot of data sets. But interestingly here, it's a strong day of the week signal in both the underlying infection process or reporting process and also in the delay distribution, which makes things a bit more complicated. This is another way of looking at it. You can see that the delays are quite extended. So there's a not insignificant amount of cases that are reported at 30 days. And also it changes over time, it changes by age. So those are things we need to consider. So yeah, to summarize this German example, we've got 7-day hospitalization incidents by date of positive test. It's a key indicator in Germany. The data is truncated, ignoring the simulated bias for fraud, well, not disease, decision making. The data is age and location stratified, and both the incidence and reporting has a strongly weekly structure, and those appear to vary over time. So the German Nowcasting Hub. This is a collaboration set up primarily by Janis Bracker and it's inspired by similar things that have been done in weather and infectious disease forecasting. So, for example, in the CDC and ECDC forecasting hubs. And it's basically looking at combining different models and as a way of improving predictions, which is shown to work really reliably. You can find this on GitHub. I really recommend checking it out. And essentially, this is collecting and combining 8 different nowcasts from independent teams and presenting a single ensemble model. And there's this nice website that, again, I recommend you check out. And you can look through the nowcast. There's also an English section if you don't speak German, like I do not. You can look through the nowcast interactively. You can explore different models. You can explore the ensemble, which is the one that's primarily used by policymakers. And yeah, so the main output here is the ensemble, and everything else is really a learning exercise for the teams. So if you're a policymaker, please use the ensemble. What do we see? We see the ensemble is generally pretty good, and that's a really good sign. Unlike forecasting, we can actually do nowcasting, which is pretty exciting because I don't know how many of you have been forecasting COVID, but for me, it's been very stressful because it's so hard. So nowcasting, yes, we can do it. That's fantastic. Sadly, we can't always do it. And there have been some clear instances where we've really failed to nowcast effectively in the hub. And unfortunately, that's also happened sometimes around decision points. So we need to know when change points are happening, and sometimes nowcasting doesn't work so well. So we need to be able to do better. So how can we do better? We need evaluation. So Johannes and the rest of the team are running a pre-registered study, so they're currently writing it up. So there's a formal evaluation, but we can also do some kind of real-time evaluation, and I'm going to present some results from that here. So firstly, I'm just going to quickly take a tangent into forecast evaluation, which is also pretty important. But basically, here we're using the CRPS, which is a type of proper scoring wall. And I'm not going to go into any details, but effectively, it's a generalization of absolute error to a probabilistic setting. We also make use of a similar version that's estimated on the log of observations and forecasts, and that gives us a generalization of the relative error. I wouldn't worry about it too much for this context, but if you are evaluating probabilistic forecasts, check out CRPS because it's a pretty good choice. So what do we see? We've got lots of models. They do varyingly well. The model I built and submitted is the EpiForecast independent model. That's one built on EpiNowcast. And unusually for evaluation from people who made models, I'm not showing you that my model's the best, which is a little bit traumatizing, but you know, it does okay. We see the ensemble is by far the best on both relative and absolute scales. That's really good to see. We see that some models do very differently on natural and relative scales, which is kind of unexpected, but interesting. We also see that in general, models do quite well with some notable outliers. Something to note here is the KIT simple nowcast is like a simplified baseline, and that on average evaluation does really, really well, which means that, well, either simple models are good enough or perhaps we are all missing something. Which I think is quite interesting. And you can see more of this evaluation at the link below, as well as the full targets-based pipeline to produce all of these results and to do the nowcast in real time. And it's pretty neat. So yeah, check it out. Although I would say that. Something we see when we look by horizon is there's quite different performance over time. So some of the models do better at shorter horizons, some do better at longer horizons. And there's obviously quite interesting nuance in why exactly that is. And something I'd point out is the EpiForecast, the EpiNowcast model that I submit, is the light blue. And what we see is it does pretty well on the relative scale, except it does pretty badly in the tail, and it does pretty badly between 7 and 9 days. So it's clearly not capturing something there. And that's also true on the natural scale. And interestingly, if we look by data positive test, we see that it was doing pretty good. And this talk was much less embarrassing if I'd given it in March. It was doing pretty good until in March, when performance really, really broke down on both natural and relative scales. And we're currently digging into why that is. Hopefully we can learn about how to do it better, but something is clearly changed. So Nowcasting Hub, it's a large scale collaboration. We found that nowcasts are generally quite good. However, most methods are a bit confident, though the ensemble is generally the best approach and is very rarely very wrong. And we've also seen that doing collaborative work enables us to learn about which methods work best, which you think would be obvious, but sadly is rarely done. So now, the EpiNowcast model. So it gets a bit complicated. I'm going to skim through the details. It's fascinating. I think nowcasting is really interesting. If you're interested, I'd check out the slides in more detail and perhaps some of the reference papers. But basically, what we're trying to do is we have this thing called the reporting triangle, which goes from untruncated data, where we know all of the counts by report, and then it goes through time where we have progressively less and less information until we get to today, where we only have a single day of report. And what we're looking to do is we're looking to reconstruct the orange here on the right-hand side, which is the part of the data that's truncated. So that's basically trying to reconstruct the orange at the bottom from the green at the top. And that's the general modeling approach. And this has been done, it's been done a lot in the literature, it's been reinvented again and again and again. I actually was just sent another new method that's revolutionizing infectious diseases, which is rediscovering nowcasting. But we have built on top of some of the work by Hole, McGow, and Gunther, who's Felix is also a collaborator here. And the idea is to separate it into two submodels. So the first model is a model for the expected number of final notifications. And then the second model is a model for the delay distribution of the reporting process. And we can split that into more models. So we can typically think about it as the baseline hazard model, the report day hazard model, and the reference day hazard model. And for those of you that know about survival analysis, I'm saying hazard. What I'm saying here is the second model is a discrete time to event model. So it's a survival analysis model. And that can be implemented as something like a Cox model, or it can be implemented as a more complicated survival model. And that is where the excitement comes in, because you get to play with all this exciting survival analysis theory in a kind of more complicated framework. And then lastly, this can all be stratified by groups, so location, age, etc. And we want to be able to potentially model that jointly or independently or in some sort of hierarchical framework. So for the expected notifications model, people arbitrarily typically used. Is that 5 minutes?
4 minutes.
4 minutes, great, thank you. So I'm just going to skip over all of this detail because it's exciting and current, but that's fine. But basically, the gist is it's really complicated, but it's really fun. And the idea is EpiNowcast is making it easier to do, making it easier to deploy, and more flexible. So what is the EpiNowcast R package? It's an R package. The idea is to be flexible. The idea is to deploy lots of different types of models. And the idea is to be able to evaluate them and to get the best model for real-time surveillance contexts. It's in development. You can find it at epiforecast.io/epinowcast. There's a nice package down site, as you might expect. It's got the core of the package is really highly optimized standard implementation that I've had a lot of fun developing, and we've got some really exciting extensions. Everything's done in the open. We have, issues, GitHub PR, code of conduct. We have all of the things you'd expect from a modern R package in development. We also have an active Slack and monthly meeting. We had it today, for example, and it was a lot of fun. And then we're also developing a series of case studies to show how to use nowcasting in practice. So, for example, the thing I was just talking about in Germany, there's a case study for that. So, yes, it's a flexible framework. It's community-driven. We're focused on optimization. We're focused on using best practices, and we've already done some real-time evaluation. Extensions. There's a lot of exciting stuff to come. We're developing a more flexible, full-featured formula interface, a better expectation model, forecasting, the ability to model missing data, and obviously a lot more survival analysis. This is a book that I enjoyed that we're basing some of our extensions on. This is an extension that Adrian Leeson is working on that's building this into a full surveillance toolkit, so backing out to the effective reproduction number, which is very exciting. And so in summary, what I presented today is a nowcasting implementation that is really important because there are so many delays between infections and what we observe, and that leads to truncations. There's been lots of models developed to look at this, and most perform quite well, but in general, they're very rarely used, and they're generally very hard to use. And the EpiNowcast R package is aiming to change that, and there's a lot of exciting development to be done. There's lots of exciting use cases, lots of exciting theory. Please reach out if interested. And here are some references. So thanks very much.
Thank you very much, Sam. So we have plenty of time left for discussion. So if you have any questions to Sam, please post them in the Q&A tab. Let's see if I can come up with a question in the meantime while everybody's typing. So does the EpiNowForecast method rely on sort of labeled data at some point? So during the sort of the training period, so to say, that we know when sort of the COVID period has onset, so that the method can discriminate between the COVID period and non-COVID period?
Basically, with nowcasting, what you're training on is the previous snapshots of observed data. So it's this idea that you have this reporting triangle, right? So you're training basically reported data. So you're training on the green, and you'd have that going back in time. So you'd have the complete filled-in reporting triangle for previous time sets, and then you're training on that to try and build out the orange. but there's nothing stopping you using other data. So, things like cases, downstream things. But yeah, you're basically training on previous versions of these snapshots.
Okay, thank you very much. There's actually a question on the Q&A from Nikos Bosse, and the question is, what would you say distinguishes the better from the worse models?
Pardon?
The question is, what would you say distinguishes the better from the worse models?
In the hub. That's really tricky. So at one stage it was flexibility. The more flexible models were doing much better. Now I have a feeling that it's a lack of flexibility because the reporting process has become so complex, and so ability to handle outliers has become much more important. And you can either do that by good outlier handling, or you can do it by not having a very flexible model that doesn't overreact to outliers. So my intuition is it's probably flexibility in both paradigms, but there's a lot more to look at there.
Okay, thank you for answering the question. There's another one which is not in the Q&A but in the chat, and the question is, oh, it has now disappeared. So I'm sure it will be put in the Q&A. Yeah, there it is. Perfect. So the next question is from Nicole Swartwood. I work on a US-based nowcasting of COVID, and we have had some trouble with the adjustment for different strains. So hospitalization rates, IFRs, all of the shifted dramatically with Omicron. Did you experience this at all with your efforts?
No. And that is because this is only built on snapshot of itself, as in it only looks at hospital admissions over time. And therefore you get away from this issue of having a generative process that goes from infection. So I think what the questioner is talking about is a more mechanistic approach. One example of a model that is more mechanistic is the RLM model that submits to the Nowcasting Hub. And that had exactly the issues he has discussed. And that's a real reason to think about which of these models so the RLM model is the blue here. So it suddenly does much worse. But the blue model is the RLM model. So it does very badly and very well in different time periods. And that's because of Omicron. So you can see it suddenly did much worse in January, and that was Omicron. And that's impact from not being able to estimate the RFR correctly. So that's why there's a lot of benefit in having simple nowcasting methods that are completely statistical, but also mechanistic nowcasting methods that are not, and then looking at both of those in tandem so that you don't get in this situation where one or the other isn't working well. And that's one of the nice things about the hub.
Okay, thank you. Let's see for another moment if there will be another Q&A question. Okay. I don't see any new question at the moment, but in case there are some questions about Sam's talk, you can always put the question in the Q&A, and then Sam can reply to it by typing the answer during the rest of the session. Okay, again, thank you very much, Sam. And then I would like to welcome our last speaker, who is Nikos Bosse. Nikos is a PhD candidate in statistics and epidemiology at the London School of Hygiene and Tropical Medicine, and he's also a research coordinator at Metaculus, I hope I pronounced this correctly. And he's currently working on infectious disease forecasting and forecasting evaluation. I'd like to give the floor to Nikos now, and you can share your slides and start whenever you're ready.
Yes, thanks a lot for the introduction. My slides now.
We can see this.
Oh, you can see me. Let me just share.
Oop.
That should work now.
Indeed, you can see your slide.
Yes.
That is perfect. Perfect. Then go ahead.
Perfect. Yes, thank you very much. My talk is going to be about forecast evaluation and specifically about an R package called scoring utils. And yeah, to give you a quick outline, I'm going to give you a quick introduction to what forecast evaluation is and what the idea behind that. Sam mentioned that already, but it's going to be a bit more introduction to that. And then I'll walk you through an example evaluation of COVID-19 forecasts with scoring utils. So why would you evaluate forecasts at all? It seems kind of obvious, but the main two objectives are to learn something about your models so you can improve them, and also to rank and select models in order to guide future. And distinguishing these two things is important because the way that you would evaluate the models might differ slightly depending on your aims. In principle, in theory, forecast evaluation is very straightforward. So there are scores that you can compute, and then good models have a good score and bad models have a bad score. But in practice, it's a bit more complicated because scores are hard to interpret in absolute values. And usually, if you have forecasts, it's hard to compare them because you have lots of dimensions. So, for example, with our COVID forecasts, we had predictions in trees over months for different target types. So it really is hard to say whether a model is good or bad because it depends a lot on the circumstances also change. You might have things like missing forecasts, and you might also have just very different formats of your forecasts. So, for example, you could have point forecasts, which just specify a number, or you might have a probability, which specifies a full predictive distribution. Targets, of course, so something might be a binary target or a continuous forecast. There are very, very many ways to store your forecasts, for example, as MCMC samples, or you could have quantiles of your predictive distribution, or just have a closed form solution of your forecast. And with all these differences, the way that you evaluate your forecasts changes slightly. And we are trying to at least mitigate that problem with our scoring utils package. But before I come to that, let's quickly talk about what a good forecast is. So ideally, you would want your predictive distribution to equal the data generating distribution. The problem is that in practice, of course, you don't really know the data generating distribution, but rather you only have a few samples from that data generating distribution. So what you do in practice in order to evaluate your forecasts is you follow the so-called forecasting paradigm coined by Tillman Gneiting and others, which says that in order to have a good forecast, you should maximize the sharpness of your forecast subject to calibration. What does that mean? Sharpness is a property of your forecast and doesn't have anything to do with the data that you observed. So a sharp forecast has a lot of probability mass centered around specific values, and a less sharp forecast is very dispersed. And of course, a sharp forecast, for example, knowing something like the temperature tomorrow will be between 20 degrees Celsius is more useful than something it will be between 5 and 35 degrees. But sharpness only helps you if your forecast is actually correct. And that's where calibration comes into play. And calibration is a sort of consistency between your predictive distribution, that's the line here, and the observations represented by the histogram. And if your forecast distribution differs systematically from the observations, then your forecasts are badly calibrated. Okay, so now there's, broadly speaking, two different things that you can do. Well, the first one is you try and look at different aspects of sharpness and calibration kind of separately in order to learn more about the specific features of your models to prove them. Or you can do something like summarizing sharpness and calibration in a single number And these are the so-called proper scoring rules. And this is especially helpful to rank models and make a comparison between models. Yeah, so as Sam already mentioned, a proper scoring rule is a rule that penalizes any deviations from the forecast to the observations. And in expectation, you get the best score if a predictive distribution F that is equal to the data generating distribution G. And the whole point about it is that it can't really be cheated. And so you have an incentive to report your best possible forecast. Okay, so there are already a few existing R packages, most notably the scoring rules package, which has a very comprehensive collection of proper scoring rules, and other R packages, which do forecast evaluation. But we still think that it's useful to have the scoring utils package because it's mostly it's easier to use scoring utils to compare other forecasts, while the existing packages usually either focus on proper scoring rules or focus on specific specific ways in which you have, for example, you can only use count package if you use something like GLM, or if your application is something like a machine learning application. But there's quite a lot of useful things that scoring utils can do that other packages focus less on. So, for example, comparing models, handling missing data. We have lots of visualizations in the package. And it's very easy to use, even as a non-expert. There's extensive documentation, and it's quite flexible in the way that it supports different formats. Okay, so now let's look at an example of COVID-19 forecasts. The example is actually part of the example data that comes with the package, and it's data from the European COVID-19 forecast. So it's forecasts for cases and deaths, and it's 1 to 3 week ahead predictions, which have been made for every week for 11 weeks by 4 models in 4 different countries. So this is a subset of all the forecasts submitted to the Forecast Hub, but it's an example. And this is what the original data look like. And you see that in the beginning, there are a few rows where you only have the data and no predictions. And then you have a lot of predictions from the different models. Okay, so in this case, we know that the data is in the correct format because it's the example data from the package. But usually the first thing that you would want to do is check your input data to make sure that it is in the correct format. And there's a convenient function that does that. So it tells you what kind of target you have, what the prediction format is. It tells you all the different dimensions across which you vary. So the forecast names, the different locations, the models. And one thing that's especially useful, it tells you the number of unique observations for every one of these categories. And for example, is that these models differ in the target types that they have. So not all models have 2 target types. And they also differ in the number of true values, so the observations. Yeah, I made it a little bit bigger so you can. Yeah, so like when we see that, it's probably useful to check for missing values, and has a nice function that does that, which is called avail forecasts, and there's a plot function for that. So you can either get everything that you want out as a data frame. There are also plot functions which the data frame and plot it. And so we can see that this model didn't make any case forecasts, and we see that this model has a few missing forecasts in these 3 weeks. Okay, so now we want to score the forecast, of course. There's a function that you can use for that, and a function called summarize scores, which is then able to summarize your forecasts. So instead of a score for every signal, you get a summarized score for per model and target type. A plot function, which once you do that, will produce a nice summary of the scores. You can see, for example,
4 minutes left.
Yes, we can see, for example, that here the ensemble tends to do very good, yes. You might want to visualize forecasts, for example. There's also functionality for that, which is really nice and convenient, and is currently used in the evaluations for the European COVID-19 forecast hub. But now, as I mentioned, we do have missing data in example. And the problem is that missingness may be correlated with performance, which means that rankings really aren't fair anymore. And one solution that we propose is a pairwise tournament between models to rank them based on their forecasts. And there's two ways to do that. There's a separate function, and there's also a pairwise comparison included in the summary function. So, for example, if we did the pairwise comparisons separately and then plotted the results, we would get something like this. I'm not going into details, but basically this is a comparison between each pair of models, and a small value means the model is better, and you get kind of some indication that, for example, the COVID hub ensemble is doing really well. And you can also do that as part of the summary function, as I just mentioned. Thing that we call a skill. So you get a relative skill score depending on on the results of the pairwise comparisons, and you also get a scaled version of that to provide a baseline. And this is 1. And if your number here is lower, then that means that the model is a lot better. And you can separately and get a separate skill score per target type. Okay, so then again, if you want to dig deeper, you can, for example, decompose some of the scores. So this is the weighted interval score, which essentially has a component called overprediction, underprediction, and dispersion. And you can kind of see what different contributors to the overall scores are, which is very nice. You can visualize calibration. So not sure whether you're familiar with pit histograms, but they are a way to just visualize how well models are calibrated. And ideally, you want this distribution to be uniform. And if it's not, as here, for example, then that tells you specific things about ways in which your model may be miscalibrated. And lastly, for example, if you want to look at correlations between scores, you could also do that and sort of see whether, for example, a good score is correlated with a lot of underprediction to have a closer look at what models do well for which reasons. Yes, so that was a very quick tour through the package, but there's a lot more. There's heat maps, there's other calibration plots, there's different example data for various forecasting formats, and detailed vignettes which help you navigate the package and really explain in detail what you have to do, even if you don't really know a lot about forecast evaluation. There's a paper that discusses all of that in detail, and it's meant to be easily accessible and help you choose and interpret different methods. And yeah, find the package on CRAN. You can find it on GitHub. You can find the paper online. And yeah, I very much encourage you to check it out. If you like to, we're very open and welcoming and happy about new contributors. there's a lot of active development going on at the moment, and we would be very happy if you had a look at it and helped make the package better. Thank you very much for your attention, and of course, thanks to all authors. This really was a team effort, and we are very happy with it. Thank you.
Thank you very much for your talk, Nikos. Very interesting stuff. We now have about 5 minutes left in the session, so if you have questions, you as the audience should have questions, please put them in the Q&A tab. So it doesn't need to be restricted to Nikos' talk, but if you have questions to the 3 other authors, please put them in there. In fact, we already have one question here in the Q&A, which is by Sam Abbott, and is, I think, devoted to Nikos. Yeah, it reads, "Great stuff, Nikos. In your opinion, what is the biggest outstanding challenge for infectious disease forecast evaluation, and can we expect to see scoring utils solving it?"
I think there's a lot of outstanding challenges. For example, a lot of the metrics that we use, and I showed some of them earlier. For example, here you can see that scores, for example, differ a lot across different forecasting targets. So cases and deaths, you see that the numbers are a lot higher for deaths. There's a problem in the fact that really your forecast timelines aren't really stationary, so things change over time. And we're currently actively looking into things like focusing more on relative errors rather than metrics that focus on absolute errors, just to be able to handle the fact better that currently most of the evaluations that are done are on some kind of absolute scale, while most of the errors that models make are multiplicative. And yeah, with a lot of with some careful thinking, utils really can help with that, and so try and help you show different facets of the scores.
Okay, thank you for your answer. Are there any more questions from the audience? If yes, please type them in the Q&A tab. Let's see. Well, some people are typing. Let's see if I can come up with a question on the spot to abridge that. You mentioned that missing values play a relatively important role in your analysis. Is there maybe an upper bound to the proportion of missing cells until things start to break down?
Yes, in some sense, yes. So what the pairwise tournament does is it compares models based on the common set of forecasts, which kind of means that if a model only has a few forecasts, then it might not have any overlap with any other model, which is of course a huge problem. But it might also mean that the focus of the evaluation shifted to where you have forecasts from both models. So yeah, we would generally not recommend to do pairwise comparisons if you have models that haven't made a prediction for at least 50% of all the forecast targets.
Okay, thank you very much. We have about 1 minute still left here in this session, so if there's still any questions left, please type them in the chat now. Oh, actually, there is some there's actually some conversation going on in the chat. From Achim Zalas. Thanks also for mentioning top models. When we finally have the package ready for CRAN, we might have a look at potential synergies. My feeling is that we focus on rather different tools, and we might add some glue to go back and forth between the packages.
Yes, I mean, so in general, my general comment is that I want this to be useful. we want this to be useful, and we're very happy to contribute our code to other packages, and are very happy about contributions from other packages. And yeah, looking forward to having that conversation.
Okay, thank you very much. So now our time is up. So I would like to close the session now. Thank you for the 4 speakers for 4 intriguing talks. And also thank you for the audience for the good questions. And in case there should be any post-talk questions, you can put them in the Q&A, and then our speakers will still be able to reply to them. Okay, thank you all very much. And I would like to close the session now by stopping the broadcast. See you and enjoy the rest of the conference.
Thank you.
Thank you.